so let's start again. So good afternoon. We're going to continue working on verified compilers. Before that, I just wanted to advertise for two nifty features of the Coq proof assistant. One is this TOTO tactic that is actually a decision procedure for intuitionistic, constructive propositional logic, and it happens to be complete. And the other is print. Then if you give it the name of a theorem, it actually shows a proof term. So, well, I don't want to spoil any lecture of tomorrow. All right, now, and this proof term is not optimal. You can find a shorter one. All right, so, pardon me? So today we are going to talk about optimizations based on a particular static analysis called Liveness analysis. And so let me start with a few words about optimizations. So it's just program transformations, so transforming the code that the programmer wrote into equivalent code that is better in some sense. For instance, it runs faster. So typically we're going to try to remove redundant or useless computations, maybe use cheaper forms of computations like this multiply by 5. So multiplication takes 4 or 5 cycles on many processors. But you can rewrite this as x shifted left by 2, which is a multiply by 4, plus x, and that will only be maybe 2 cycles. And also it could run faster because it exhibits more parallelism, either at the level of instruction or even at the level of threads. But for other devices, you may have other objectives for optimizations, like maybe you want smaller code for cheap embedded systems like smart cards or RFIDs, where memory is at a premium, and if you can shave 1 kilobyte of code, maybe you will improve your profit by 1 cent and sell millions more. Maybe you want to optimize for energy, especially for battery-powered systems like smartphones. Or maybe you want to have code that is more resistant to attacks, in particular, observation or perturbation attacks, so security attacks. That is typically the case for smart cards or cryptographic coprocessors and other highly secure systems. So, and optimization is a misnomer. I mean, it's very rare that the code you get out of a compiler is optimal in the sense that you can't do any better, okay? It's just better, okay? And so there are dozens of compiler optimizations that are known. You can find that in compiler textbooks, each targeting a particular class of inefficiencies. And good compilers like GCC run maybe 100 optimization passes, just trying to make your code better. And there's a deep connection between compiler optimization and static analysis. So there are optimizations that are unconditionally valid, always valid. Like multiply by 2 being replaced by an addition, or multiply by 4 being replaced by a left shift by 2 bits, at least if your computer runs in binary. But for most other, you need to know something. You need some conditions to be met in order to apply the optimization. For instance, a divide by 4 is equivalent to a left shift by a right signed shift by 2. But only if x is positive, because if x is negative, this rounds down and this rounds, this rounds down and this rounds towards 0. Even simpler, if you know exactly statically the value of a variable, then you can, like x is 0, you can pre-compute whole expressions, like x plus 1 becomes 1. If you know that a test is always true, for instance here, then you can remove the other part, you can remove the test and the else branch. And this is the one we are going to look at today. You can even remove whole assignments, whole computations, if you know that the variable, the x that contains the result, is actually unused later, okay? And so in general, you need a static analysis prior to the actual code transformation. And so, again, what is static analysis? Well, its purpose is to determine some properties that hold of all concrete executions of a program. And very often, these are properties of the values of variables at a given program point. For instance, at this point, we know that x is equal to this constant, compile time constant, that can be determined by the analysis, or x is in this interval. And again, these are two compile time constants. Or maybe x is equal to this symbolic expression. Or maybe we have some kind of linear inequality connecting the values of x and y, with a, b, and n being compile time constants. So we'll talk more about that tomorrow, but basically the basic requirements of a static analysis. So well, whatever it infers must be true for any inputs to the program, okay? And the analysis must terminate, of course, and it must run in reasonable time and space. Because we are not going to wait 24 hours for our code to compile. And so this is the running example for today. That's dead code elimination via Liveness analysis. And so we want to remove assignments of the form x gets e and turn them into skip statements whenever the variable x is never used later in the program execution. And here is an example. You assign 1 to x, then do some computation that doesn't involve x, then reassign a new value to x, okay? This assignment is useless. If you remove it, nothing changes because this computation doesn't use x, and at this point, and from this point on, x has a new value, which is 2. And so this is the kind of things we want to optimize, and for that we need a static analysis called liveness analysis. So let's start with that. So variable is dead at a program point if its value is not going to be used later in any execution of the program. Maybe the variable is not mentioned again before going out of scope, or it will always be redefined before being used, okay? And that's really, so this variable x is dead at this point. Because it's always going to be redefined before being used. And conversely, a variable is live if it's not dead. And for straight line programs, sequences of assignments, like my example, this is fairly easy to determine, to compute. So variable x starts initially dead, becomes live at the first definition, that then stays live until this use. And now there's no further use before a redefinition, so it dies, becomes live again at that definition, stays live because of this use, and dies here because this is the last use. Okay? So very easy to spot just by looking at the code. Now if you have loops or if then else, it's a little more delicate because, for instance, this is an if then else with the two branches that eventually merge, and with some definitions and use and redefinition and use, and we see that actually the variable is, well, it's live. From this definition on, it's live because it may be used here, although on that branch, this definition will not be used, but we must be conservative. So we'll say that it is live here, and again, all the way down there. And from this definition, it's also live because we have a use that we can reach, and it's only dead before, between this if and this def. So as usual with static analysis, we are going to be conservative and over-approximate, assuming, for instance, that all conditionals can be either true or false, so both branches are taken, and all while loops are taken 0, 1, or several times. And so this is how we compute liveness information. So the set of live variables at any program point is basically by solving those equations. So these are called data flow equations in the literature. And it's even a backward data flow problem because basically, given a command C, we are going to compute the variables that are live just before C as a function of the variables that are live just after. Okay? So in a way, we are tracking the flow of uses backward, starting from the end of the program and moving towards the beginning. And so there are easy cases. So if the command is skip, it doesn't use any variable, it doesn't define any variable, so the set L doesn't change. The interesting case is assignment. So in general, we are going to use some variables, those that are free in A, okay? So those variables better be alive before this assignment because we are going to use them. And then we are defining X. So if we are using X after, X is in L, we are defining it right now, so it doesn't need to be live before. Okay, so basically we are removing X from L, but any other variable that is used after, that is in L, must also be live before. So that's really L minus X, to which we add the free variables of A. And that must be done in this order because if X is mentioned in A, it's an X that was defined before, it's not this X. So this order is important. And then we can optimize a little. Notice that if X is dead, X is not in L, X is not used afterwards, we will going to turn this assignment into a skip. And so we can analyze this assignment as if it were a skip and not add anything to L. Okay, so for a sequence where we just track the flow of information backwards, so from L at the end of C1 we have live of C2L, which must be live, and so at the beginning of C1 and at the beginning of the sequence all this must be live. For an if then else, as I said, we consider both branches to be taken, so we just take the union of live variables before C1 and C2, and then we add the variables free in B because we need them to compute the test. And the difficult case is a while loop. And basically, we want a set X that satisfies this set inclusion. And let me try to give you some intuition. So this is a while loop that I have unrolled a few times. Okay, and we are looking for this X here, which is a set of variables live before the while loop. So two things are obvious. First, we need to test B. So all variables live in B, free in B must be in X. That's condition number one. Second, if B is false, we are going to exit immediately to after the loop. And after the loop, everything that is in L must be live. So L must be a subset of X. And then what do we do if we iterate? Well, we are going to execute C, and at the end of C, we are going to redo our test and so on. So at the end of C, the set of live variables is X again. So before C, it is live CX, and that must be included in X. Okay, so we've got those three conditions that must be satisfied. And that's a fixed point problem. Okay, basically we have to solve for X in this equation or inequation. And that corresponds to taking the fixed point of this functor, if I may say so. So basically a function from sets of variables to sets of variables. So a fixed point would be best for maximal precision. For correctness, it suffices to get a post-fixed point. So something that is such as f of x is included in x. And well, there are basically two ways to go about computing fixed points. There are the mathematicians and their approach, and there's the engineers approach. So we are going to see both today. So very quickly, the mathematician's approach, and then I'll come back to it, is to invoke the Knaster-Tarski theorem, which says that if you have a function functional from A to A, where A is a partially ordered type, then with the smallest element bottom, then if you iterate f starting from bottom, so bottom, f of bottom, f of bottom, etc., after a while you will converge to the smallest fixed point of f, providing that f is increasing, monotone, okay, compatible with the order, and your partially ordered type has the chain condition, which is that all strictly ascending chains are finite. So you can't grow infinitely. At some point you will have to stop, okay? And this is why this sequence eventually converges. And so we'll come back to that approach later. It is beautiful. It is very interesting to program in Kirk. However, it is rather difficult, so you have to formalize and exploit this ascending chain property, and that gives rise to well-founded orderings and Noetherian induction. And in our case, liveness analysis, so our ordering is strict inclusion between finite sets, but it does not obviously have the chain condition. Okay, by adding new elements, you can always grow and grow and grow. And so we'll have to argue that no, it is not possible for this particular fixed point computation to go forever. And for that, we will need some dependent types. So that will be for the end of the lecture. Right now, let's switch to plan B, which is the engineer's approach. Well, it starts like Tarski's. Compute f of bottom, which is the empty set. So f of the empty set, f of the empty set, up to some fixed number of iteration. So if you find a post-fixed point in this sequence, okay, some I such that this inclusion is met, then you have a solution, so you stop. Otherwise, you will return a safe over approximation. And in our case, for a while loop, actually, this set is a safe over approximation of the live variables. And then you can choose n appropriately, or maybe, I don't know, 10 million. Anyway, if your compiler hasn't found a fixed point after 10 million iterations, maybe it is time to switch to a safe over approximation, okay? And in practice, those fixed point computations converge much more quickly than that. So your chances of finding it by the engineer's approach are extremely high. All right, and let's see how it looks like in code. All right, so yeah, so we need sets of variables. So there's a nice library in the Coq standard library for finite sets and finite maps, which is presented as a so-called functor or functors. So in the sense of ML, standard ML or camel functors. So it's basically a glorified function. Okay, but instead of taking values and returning values, it takes structures, so-called modules, which are collections of definitions and lemmas and so on, and produce a new set of a new structure, a new set of definition and lemmas. So here, this functor fsetavl.make takes a so-called order type as argument, which is a type. In our case, that's the type of identifiers, equipped with an equality and equipped with a total ordering. So there's an equality EQ, there's a less than ordering, which is basically the order of integers, and some properties about those orderings. And the fact that it is decidable whether two elements of type T are equal or less than or greater than. Okay? And based on that, this nifty library gives you a rather efficient implementation of sets with balanced trees, log time operations, and a whole lot of properties about set operations, which are very useful in our proofs. Okay, then we define, using those sets, we define the set of variables appearing in an expression or command, so the free variables. And the definition is kind of obvious. Okay, it's empty for a number, it's a singleton set for an identifier, and for a compound expression is the union of the free variables on both sides. Likewise for Boolean expressions, and likewise for conditions. Okay? So this is the post-fixed point computation I mentioned. So we take our function f from sets to sets. The default result we return if we run out of time, and then we iterate at most n times. So if n hits 0, then we return the default. Otherwise, we compute f of x. If f of x is included in x, then success. Otherwise, we iterate with the predecessor. And here I'm saying, okay, iterate 10 times, and starting from the empty set. And so we have this characterization that either we have a post-fixed point or we get something that is equal to the default. And yeah, if we have some more hypotheses over f, we can show that the result is always at most as big as the default value. All right, and so this is a computation of live variables. Basically a transcription of the equations I showed you. Okay, that's a command, that's the variables live after. It returns the variable live before. So for skip it's L. For an assignment we have the two cases, whether X is live after or not. For the sequence we just compose. For the if then else we consider both branches taken. And for the while we invoke our fixed point computation with this carefully constructed function. Okay, so fairly simple transcription of the data flow equations. And then we can prove some simple properties, in particular that for while loops, we indeed, the value we compute indeed satisfies the three conditions I showed you on this diagram where I unrolled the loop. Okay, so free variables of B are in L prime, and L is in L prime, and live CL prime is in L prime. Okay, so it takes a little bit of proving, but not too much. All right, so now what are we going to do with this liveness information?